did our first try, we got one solution, but not the best solution. The first try, we find the minimum first, so we need n-1 comparisons based on our, our first selection problem. It's optimal, so we use it here as the first step, n-1 comparison. But in the second step, when we find the maximum, first we know the minimum can be excluded because the minimum cannot be the maximum. So by elimination method, so we can, reduce the problem size by 1. But after that, we just apply our, finding the minimum, but we switch to the maximum version because they are essentially the same, right? We just switch to the maximum, change the direction. So we find the maximum with n-2 comparisons. We add up, from number of comparisons from these two steps. So our final answer is this method we need 2n-3 comparisons. After that, we do analysis. So we feel this way is not the best way. The reason is when we do the second round, finding the maximum, the second round, we throw away the information collected from the first round. First round, you did n-1 comparisons. Can you reuse that information, right? n-1, we collect a lot of information. Can you reuse the information from the first round? Then you can save some comparison in the second round, right? The idea is like that, but the question is, how do you reuse, right? If you cannot keep track of the comparison results, how can you reuse existing comparison results, right? Yeah. So the question is, it's not easy to keep track of the comparison result. Yeah. So that tells us how to improve from this analysis. Okay? How do we improve? How do we find a way to help us keep track of the comparison results better than before? That's the question. Our old way, because the old way, the data organization part is not good enough. So we couldn't keep track of the data we already derived, right? You derived the data, but very messy. You didn't organize your data well, so you cannot preserve the known results, known comparison results. Yeah. Now we want to find a better way to organize the data such that we can keep track of the known comparison results better. How about that? Yeah, that's the idea. But how to organize your data better? Yeah. You need to use some special method to organize your data better, right? Yeah. Here, the special method we organize. Yeah. I mentioned last time, the tournament method. Tournament. That's the way we organize our data, right? In the sports games, people use the tournament method. Yeah. Why? Because using the tournament method, the organizer, they can organize the players well, right? Yeah. So here, kind of data organization. Yeah. Do better organization. That's the purpose of that tournament method. Okay? Yeah. So here, other than this elimination method, we need to add another important method, tournament method. Tournament method. method, right? Yeah. All right. Now, let's do the work. Yeah. So all right. So to do the work, I write in this way. Okay. Yeah. Yeah. Here, in order to reduce our sentences, words, description, yeah, because we don't want to write a lot of words. Okay. So here, because our main goal, we want to represent the idea, right? Idea is more important. Yeah. So we use diagram to represent the idea. Okay. Yeah. So we can use the graphical way to draw diagrams to represent our idea. Yeah. Tournament method. I use diagram to do the tournament method. All right. The first pair, yeah, I organize first pair x1, x2. Yeah. The first pair of players or elements. Okay. All right. But one, on top, one at the bottom. Yeah. Top, bottom. Yeah. Because I use the different locations to represent winner and loser, right? Yeah. Winner, loser. Winner, top row, okay? Loser, bottom row. Yeah. All right, so that's the, first pair. Yeah. All right, then next, x3, x4. Okay? x5, x6. Dot, dot, dot. Okay? Remember, we assume n even, okay? N even. N even. And we can use 2k, how about that? Even we can represent as 2k, okay? All right. Then, the last pair, x 2k minus 1 and 2k, okay? Yeah. So we pair them like that. How about that? Okay? Yeah. Then they play each other. Yeah. But top and the bottom, for simplicity, because one at the top, one at the bottom. For simplicity, we put the elements with all the subscripts, top row, because that's not important, right? Just one higher, one lower. The specific, not that important. All right. Yeah. Then, the first round, how many comparisons do we need in the first round? Then, all these, each pair, we do one comparison. So, we complete, the comparisons for all these pairs. How many comparisons do we need? That's the first round comparison. How many? Yeah, n divided by 2. Yeah, here you can use k. Okay, yeah, n divided by 2. Yeah, so k comparisons. All right, after that, then we need to do second round comparison and third round comparison, right? All right. Yeah. Before we do the second round comparison, yeah, here you assume top row winners. So this top row, all these players, they're winners. Current winners, okay? Yeah. All these players or elements, they are current losers. Okay, all right. Then, in the second round, because we need to find a maximum and a minimum, right? Maximum and a minimum. Now, based on the information we collected so far, when you find a maximum, what do you want to do? What type of comparisons do you want to do when you need to find the maximum? Yeah. Here, let's just consider maximum first. Yeah. Yeah. Don't look at the minimum. Okay. When you find the maximum, where should you look for?
You're saying for the second round of comparisons.
Second round.
We'll just take the top row.
Yeah, top row. Because we can see the maximum cannot appear at the bottom row, right? Because they're losers. How can one loser become a maximum, right? So this analysis helped us eliminate 1/2 of the players, right? That's a lot of elimination, right? 1/2 of the losers are eliminated in the second round. Yeah. The more elimination you can do, the better the overall performance, right? Yeah. Here we eliminate K. Okay? So you only need to do comparison at top row. How many comparisons do you need to find the maximum in top row? Okay? Yeah. Yeah. So this is the first round. K comparisons. Second round. Okay. Second round, 2 steps. Okay. For max. How many comparisons? Only do comparisons at top row to find the maximum. You know the number of elements in top row, right? Yeah. How to find the maximum? How many comparisons?
That would be K over 2 versus the second one.
Given n elements, we need to find the maximum. How many comparisons do we need? Given n elements. Given n elements, we need to find a maximum. Yeah, just borrow the result from the minimum. Given n elements, find the minimum. You know the answer, right? Finding the minimum. Minimum. N minus 1. Max, the same number, right? Yeah. Here, we change n to k because we have k elements in the top row. So we need to find the maximum. How many comparisons? K minus 1. So here we k minus 1 comparison. Similarly, for the minimum, do you want to do the same thing? Minimum, you only do the comparison at the bottom row, right? Yeah, because the winner cannot be the minimum, right? None of the winner in top row could be the minimum. So you eliminate all the elements in the top row. That's a lot of elimination. Then, yeah, by the same conclusion, k minus 1 comparisons. Yeah. Then combine them together. Yeah. You know, yeah. Combine them together, or you combine, you know, all of them. K plus k minus 1 plus k minus 1. You have 3k minus 2, but the k is n over 2. Yeah. So 3n over 2 minus 2. Yeah. But that's for the even case. N is even number. You have this answer, this formula. After that, you need to consider when n is an odd number. Odd number because you already have your solution for the even case. When you consider odd case, can you modify this current solution? Yeah, that's because we have a lot of related work. This is a related work, right? Yeah. Odd, the difference is small, right? Yeah, because the last element, you don't have that pair, the last element. Yeah. For odd case, so here, n is odd case, So you have a, you can assume n equals 2k plus 1, right? 2k plus 1. Can you imagine you have a singleton element x sub 2k plus 1, extra singleton element 2k plus 1? When you do the tournament method in the first round, the last player cannot be grouped with any other player. So the last player is idle, okay? Idling, yeah, idle. The last player, but in the second round, do you think the last player automatically qualify for the second round? Yeah, right? The last element, yeah, so here, the last one, because the first one, the last element does not play in the first round, so there is no way you can eliminate the last element in the first round, right? Yeah, because you don't have information to eliminate that player, right? So this player is lucky, it automatically goes to the second round. Without play, automatically goes to the second round. In the second round, when you search for the maximum, do you need to consider this last element? When you look for the maximum, do you need to consider the last element? You need it, right? When you search for the minimum, do you need to consider this one? Yeah. So you need to consider this last element in two situations, the maximum case and the minimum case. Then you know how to do it, right? Yeah. Put all these pieces together, you can get your final answer. You can get your final answer. Matthew, can you tell me the final answer?
The number of total comparisons.
Yeah, using K. Just use K.
It would be 3K for total.
Good, great. 3K. Kirill, is it correct? 3K. 3K. Yeah. Because first round K, still, we keep that. First round K, we do not change anything. But the second round, these two cases, we need to modify from K minus 1 to K, right? This case, we need to modify from K minus to K. So K appears in 3 places, total 3K. 3K. Then you convert it to, yeah, because K equals n minus 1 over 2, right? Then you convert to n, yeah. Because here, K equals n minus 1 over 2. So 3K. You should replace K by this number, n minus 1 over 2. Some people use the floor function, ceiling function. Then you can write one formula. Okay? Yeah. Think about it. Yeah. Because for this class, we use the floor function, ceiling function a lot. When we have even odd case, sometimes we want to write one formula. One formula, yeah, you need to think about, can we use a floor function or ceiling function? We only need to write one formula. Okay, floor function, ceiling function. Yeah. Here it's like floor function. Because n minus 1 over 2. n minus 1 over 2. Yeah, so here you consider both n minus 1 over 2 and n over 2, are they the same floor function of n over 2? For both even odd case, floor function of n over 2. Yeah, so the floor function of n over 2 covers both cases. Okay? When n is even, that's this. Okay? When n is odd, it's that. Okay? Same formula, you cover two cases. Two cases. Yeah. Yeah. Because it's more convenient, right? we use one single formula, okay? Flow function of n over 2. More convenient, okay? Yeah. Things like that, okay? Yeah. All right. Same formula. Yeah. All right. So we solve this problem. At the end, I want to tell you one final result. At the end, final result. Yeah. Other than this number, this formula is the main result. But other than this one, the final conclusion. This method is optimal. This method is optimal. That's the final conclusion. Optimal. That means nobody can improve this formula anymore. Okay? This is the best formula people can get. Yeah. Nobody can improve this. Yeah. There is a proof. Yeah. The proof, out of scope for this class. Yeah. 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 It's not easy, but it's available. The proof is available. Okay. If you want to know, so you can find it. Yeah. I can give you a reference if you want to find it. Yeah. Yeah. So optimal. Yeah. So we complete module 1. All right. Any question? No. Yeah. I'm working on project 1. I need to modify the requirement. So I expect to make it available in 1 or 2 days. Yeah. Okay. Yeah. Sorry. Yeah. Sorry. All right. Just to let you know. Yeah. All right. Yeah. So that's the old topic. Yeah, the new topic today, part A. Module 2, part A. All right. Yeah. Okay. All right. The topic of Module 2, analysis of algorithm efficiencies and the brute force method. The first part, analysis of algorithm efficiencies. Yeah. So remember last time, one student mentioned that big O notation. Yeah. In this module, we need to learn that big O notation. Yeah. Very abstract. Yeah. But that notation is so important. So we have to understand the basic idea. All right. Then, brute force method, we already used the brute force method in module 1 in our polynomial evaluation. The first method is the brute force method. But here, so we just, understand a little more of this method. All right. Part A, the topic, problem solving from experience and elimination method. So we need to solve a new computing problem, 8.1 selection sort. You can see this is our first sort algorithm. We have 3 basic computing problem types. Yeah. We did 2 already. Yeah. Search. Yeah. We did that linear search. Yeah. Selection problem, we did that finding the minimum. Yeah. First one. Now we need to work on our first sort problem. Yeah. Selection sort. Okay? The first one, selection sort. Yeah. All right. So let's look at the question first. Our problem number 4, sort an array. Given an array, unordered, we need to make it ordered array. How to sort it in ascending order? See, the question very short. We need to sort it in ascending order. Yeah. All right. Okay. Here, the title, remember, title for the part A, problem solving from experience. Here, we do not need to look other, places, very complicated. So let's just search our experience. We get it so far. Yeah. The experience, module 1, that's our experience, right? Yeah, everything we learn in module 1, that's our experience. Can you use the knowledge we learned from module 1 to solve this problem? Yeah. So that's the problem solving from experience. Yeah. Yeah. All right. Yeah. So let's do it in that way. All right. The problem type, so here I give you the reference, section 3.1. All right. Work and analysis. Yeah. Now, here is the problem 4. Before this problem, there are 3 problems we completed. Problem 1, 2, 3. Those 3 problems, that's our experience. So when you need to look at your experience, look at these 3 problems. Which one is closely related to this one? You feel you can use that result to solve this one. Yeah, we have 3 problems. First, polynomial evaluation. Can you use polynomial evaluation here? No. Second one, linear search. Can you use the linear search here? Linear search. Linear search, given a search key first, right? What's the search key? Because when you need to find an element, you need to have a search key first, right? Here, sorted, there is no search key. What's the search key? Right? Yeah. So we can skip that second problem. The third problem, finding the minimum. Do you think that question, our problem number 3, is related to this one? Think about it. Possible, right? At least, yeah, we can explore. Yeah. So here the question, because first thing you can see among these 3 problems, the third one, problem number 3, is the most related to this one, right? Yeah, the closely related to this one. Yeah. So next question is, how do you apply the result of our problem number 3 to solve this problem? That question. Problem number 3, finding the minimum. How to use the solution, finding the minimum solution to solve this problem. That's the key. Yeah. Yeah. That's our direction to go at this point. All right. Yeah. Yeah. All right. Yeah. So here, in problem solving, it's very common we use backward thinking. Okay, backward thinking. Yeah. Yeah. Because right now, we're in the understanding stage. Analysis and understanding. We want to understand our situation, right? Yeah. So we do a lot of mental exercises, okay? Mental work, mental analysis work to get ourselves understand the problem better and better. Better, we want to explore new properties when we understand the problem. Okay? Yeah. Now, so we use the backward thinking to try to explore some new property. What's the backward thinking? You assume you already have the final result. That's the backward. You already reached the end, then you're going backward. Okay? Going backward. Our destination, the whole array is sorted, right? That's our destination. Yeah. So we start from our destination. We assume the whole array is sorted. Let's take a look. Can we see any new property? So if we look at if we assume the whole array is sorted, can we find some interesting properties? Yeah. So here, for simplicity, we assume the elements distinct. Yeah. For convenience. Yeah. Yeah. Here, let me give you another. So why? Yeah. Because in the original question, there is no such assumption, right? Yeah. Yeah. So here, let me explain the point. Yeah. Why the original problem, there is no assumption, the elements are distinct, that assumption, but we can assume it's distinct first. Yeah, let me give you the justification. Yeah. In problem solving, it's very common. Okay. All right. If you recall, okay, so one of the previous lectures, I talk about one idea, and I said that idea, people call it the golden rule. Remember, I mentioned this phrase, golden rule phrase. Yeah, so here, we use that golden rule again. Okay. So what's that golden rule? Yeah. Yeah. When you solve a problem, you have, many different cases, different situations. When you start, always start from the simplest case, right? That's the golden rule. Yeah. We have even order two cases, and even case is easier. So you should start from the easiest case, even case. At that place, I mentioned this golden rule. Okay? So here, we have a similar situation applying this golden rule. What's that? Yeah. So the data is not necessarily distinct. But do you feel the distinct element, that's the easiest case? Yeah, the distinct element, easiest case, right? Yeah. So then, based on the golden rule, we want to work on the easiest case first. That's the justification. Okay? Yeah. After we find a solution, then we remove that assumption. How about that? So if elements are not distinct, we modify our first solution slightly, yeah, we can get a second solution. Okay? Yeah. So that's the reason we can make this is a reasonable assumption. Okay? Yeah. Based on the golden rule. Yeah. All right. Yeah. So assume distinct elements. Yeah. All right. Then let me, because our goal, we want to make connection. Yeah. Yeah. How to apply the solution of problem number 3, finding the minima, to this problem. And this still looks, there is some distance, right? Yeah, not very close. Yeah. So we want to, when we connect these two problems, number 3, number 4, let's make them closer and closer. Yeah. All right. So to make that, yeah, let's use a simple diagram. Yeah. From this simple diagram, you see the data is sorted, right? The data is sorted. Now, when you observe the sorted data, what is the minimum? What is the minimum?
0.
Yeah, x0, the first element. The first element in the sorted array is the minimum. Is that connection? Is that connection? Yeah. That means, so you change the way you ask your question. All right. So the obvious question is, when you have a sorted array, the first element in that ordered array is the minimum. Can you go in opposite direction? Where you find that minimum, is that minimum should be the first element in the final sorted array? You ask question in the opposite way, okay? Yeah. Backward thinking, right? Yeah, you change the way to ask question. Yeah. All right, let me repeat that question again, all right? Yeah. All right. So when we start, yeah, because based on observation, the minimum should appear as the first element in the finally sorted array. Yeah, that's obvious. All right. Now, we change the way to ask this question. Okay? All right. If we can find the minimum, we know how to find the minimum, right? The problem, result problem number 3. That's why we connect. Okay? If we can find the minimum, is that minimum should appear in the first position in the finally sorted array? Thinking that way. Yeah. When we find the minimum, we know how to find. We have the confidence, right? Yeah. Now we have the confidence. So after we find the minimum, where should we put that minimum element? Where should we place it?
The very beginning.
Very beginning in our destination array, right? Yeah. Because our goal, we try to generate the destination array. The destination array, all the elements are in ascending order. That's the, the situation of the destination array. Then the minimum element should appear as the first element in our destination array, right? Yeah. Do you feel you can make some progress? Yeah, right? Is it some progress? Yeah. All right. So now you know which element is the first one in the destination array, right? Yeah. After that, can you find the second element in the destination array? After that first one. After the first one, you can eliminate it, right? Yeah. It is out of the consideration. But after that, can you find the second element in the destination array? Right? After that, can you find the third element in the destination array? Fourth, and so on. All the way to the end. In that way, can you find all the elements in the destination array? Right? Yeah, that's the main idea. That's the main idea. All right? So let's, here you can see how to find a solution. Yeah. How to apply our old solution to solve the new problem. Okay? All right. Yeah. So finding the minimum, you get the first element in the destination array. Okay? All right. Yeah. So here we need to use a new concept called an in-place concept. Yeah. So what's that? Yeah. I think from the language, the meaning. Yeah. But here, yeah, because this minimum, we know it should appear as the first element in the destination array. So we can place it in the first location in the destination array, right? Yeah, because at the beginning, our destination array is empty. Okay, nothing there, right? So the first element, we put it in the right place. That is the minimum. Okay? Yeah. So that element, we put it in the right location, we call it in place. We put it in place. Okay? Yeah. Yeah. All right. Then, after that, we can put second element in place. Then third element in place. Okay? Fourth element in place. Yeah. Every round, we put one element in place. Yeah. Every round, we apply finding the minimum solution so that we can put one element in place. Yeah. Now you tell me, how many rounds do we need to work to put all elements in place? First round, we put one element in place. Second round, two elements in place. Now we want to put all the elements in place. How many rounds of finding the minimum, that solution? We just call it, okay? We have that solution, we call it. How many times do you need to call that function, finding the minimum, that function? Great, n minus 1, not n, okay? Not n. Because after you call n minus 1, only one element left. that must be in place, right? You can put it without calling the function, right? Because that's the only one left. And in the destination array, the last location is empty, right? That's the only place you can go. So that's the only place you can place the last element. And you don't need to call that function, okay? So n minus 1 times, okay, we apply that solution, finding the minimal solution. We can get the whole array sorted. Okay? Yeah. So we call this sorting method, we call it selection sort. Why selection sort? Because finding the minimum is a selection problem. Right? Finding the minimum is, we call it, it's a special selection problem. Yeah. So you apply the solution of a selection problem to sort the array. So for that reason, we call it selection sort. Okay? All right? Yeah. Yeah. So you can see, you know, all this kind of analysis. All right? Yeah. Here we apply the elimination method because every round we eliminate one element from the consideration. So that's the way to apply the elimination method. Yeah. Yeah. All right. Yeah. Yeah. So the next minimum and so on. So each round we place one element in place. But we do not need to do it for the last element. Because no other choice, right? Last element. Only one place to go. No other option. Yeah. No uncertainty, right? Yeah. No uncertainty. Why you need to do redundant work, right? There is no uncertainty. Yeah. So nothing you need to do. Yeah. All right. So then, yeah. So actually here we already went through the whole process. Okay. Every time put one element in place. Then so we have that. Yeah. The conclusion. So where all the elements in an array are in place, this array is sorted. Yeah. All in place. Okay. So order, ascending order. All right. Then we need to do one thing. Yeah. I need to look at the time. Yeah. Okay. I still have some time. Yeah. All right. Efficiency analysis. We want to see when we apply the selection sort, how many total number of comparisons do we need? We need to calculate the total number of comparisons. All right, yeah? Let's count the number of comparisons. Because finding the minimum, we know each round how many comparisons, right? Yeah. Finding the minimum, we know the number of comparisons. Yeah. All right. Finding the first minimum, we need n minus 1, right? Finding the second minimum, we need n minus 2, and so on. Finding the last minimum, we need one comparison, right? Yeah. So you add up these consecutive integers from 1 through n minus 1. Then we apply summation formula, yeah, well-known summation formula, so we get 1/2 times n minus 1. This many comparisons. Yeah, so we get an answer. Total number of comparisons. That formula, okay? All right. Yeah. After that, then we need to consider these 3 cases. Remember, in the linear search, we look at these 3 different cases. Now, can you tell me when we apply this selection sort, what is the best case? Best case means you can imagine the data for what kind of special data you get a minimum number of comparisons. For different data, yeah, because the we know the data, given data, there are many different cases. For the general sorting algorithm, for some data, you need a fewer number of comparisons. For some data, you need a more number of comparisons. But here, can you see any difference? Yeah. So here, for any data, you get the same thing. You get this many comparisons. No difference, right? For any data. All right, so here, let me ask you. If the data given is already in ascending order, yeah, we can assume that, right? That's special case. Let's assume the given data is already in ascending order, okay? Yeah, so the given data already in ascending order, that assumption. Do you think we still need this many comparisons, 1/2 times n times n minus 1? Do you feel you still need this many comparisons to get it sorted? Think about this question. Yeah, the data ordered, already in ascending order. Do you need to still apply 1/2 n times n minus 1, this many comparison to get it ordered? Cody nodding. Yeah. Cody said no. How do other students, how do you feel? Because it's already sorted. Why you still apply? You know, this number is pretty big. 1/2 times n times n minus 1. Based on our assumption, it's already sorted. Why you still need to do some, you know, unnecessary work, right? Unnecessary comparison work to make it sorted, ordered. And can anyone say something? Say something, John.
If there's repeated
Repeated value, let's assume no repeated value. Okay? No repeated values, right? Yeah. Because this question, in this class, we need to, you know, we need to touch this point many, many times. Yeah. Yeah. It's an important point. Okay. Yeah. It's already sorted. Cody, if you know the data is already sorted, can you leave it there? Just leave it there. Do nothing. Is it okay? Other students make some comments? Yeah. It's already ordered. Yeah. All right? Is it okay? Yeah. Because it's an important question for this class. Okay?
I think we should check.
Good. Kiri pointed out an important point. Yeah. So here, yeah. All right, Cody. So here, let me describe the whole situation a little more clear. Yeah. Here, we assume it's ordered already. Okay. Assume it's ordered. Yeah, that's possible. But the question is, how do you know it's ordered? We assume it's ordered, but you cannot see it. The underlying data is ordered, but you don't know. That's why he said, you need to check it. Okay? Yeah, that's a great point. Because if you do not check it, how do you know it's ordered, right? You need to check it. Yeah. But the question is, how much more effort do you want to pay to check your data? You need to do some work, right? How much work do you want to do to check your data? Checking, that's a lot of work, right? It's not free. It's a lot of work. Yeah. So in the real world situation, we do not check. We do not check. Okay. we do not check. No. Nobody check it, all right? No. Because the cost is relatively high. Okay? The long-term, especially long-term cost, all right? You consider, all the situation combined, the long-term cost, you waste your computing resource to do it. We don't want to do that, right? So without checking, even it is already ordered, but you cannot assume it's ordered. Okay? You treat it as unordered data. So when you apply this algorithm, you just apply it on some unordered. But when you do it, the first is the minimum, second is the second minimum, second smallest. Keep doing that. It looks like, but that's just you have to do it in that way. All right? You have to do it in that way. No swap, okay? No swap, you just copy your data. Because you do not know if the data is ordered and you do not want to check it. Long-term cost, you feel no checking way is better for long-term cost. The checking way, long-term cost is higher than no checking way. Okay? So that's why people don't do checking. Okay? Then you don't checking, you need to do all the comparisons. All right? Yeah. Another, because later we will have similar, here I spend a lot of time. But another place, okay? All right. When we say the data is ordered, all right? For human, we have an idea the data is ordered. We can see it, right? For human, yeah. But for computer programs, when we talk about computer programs, the computer does not have eyes. Okay, the computer cannot see the data. Okay? Even your input is ordered, but the computer does not know it. Okay? No eyes. You cannot expect the computer can see the data. All right? No. The computer can see nothing. Okay? Yeah. If the computer needs to know something, it needs to do some checking work. Okay? If the computer does not do any checking work, computer knows nothing about the data. All right? Even the data is ordered. Computer is blind. Okay? Yeah. You still need to run the algorithm from beginning to end. Okay? Yeah. Even the data is ordered. All right, next. Now summarize elimination method. So at this point, we apply this elimination method several places, right? Yeah. You can see, yeah. So far, this is a very important. It's simple, right? Yeah. Because it's so obvious. Yeah. So obvious. Yeah. But it's simple, but very effective. Very effective. Okay? Yeah. So here, let's summarize a little bit. Yeah. The goal. Yeah. Why this method is useful? Yeah. Because this method can reduce the problem size. When you eliminate certain number of elements, you reduce the problem size a little bit, right? Yeah. Size reduction. The idea is the size reduction. If we can reduce the problem size, we can make our solution easier, right? Yeah. That's the point. All right. The smaller the problem size, the easier the problem. That's our intuition, right? When you need to sort an array with 1,000 elements, you need to do more work, right? Comparing, you sort an array with 10 elements. Which one is harder? Okay, that's so obvious, right? The problem size is larger, you need to do more work. When the problem size is smaller, you need to do less work. Okay, yeah. But that's intuition. That's the intuition. Do you feel this statement is true all the time? This statement is true all the time? That question, yeah. Kirill said, not all the time. Okay? Can you imagine in some special situation, this statement may not be true? This statement may not be true in some special situation. That means when the problem size is relatively smaller, it's harder than the problem size relatively large. Is that possible? When the problem size is smaller, the difficulty solving that problem is harder than the problem size relatively larger. A little larger. Is that possible? The answer is yes, it's possible. It's not possible. So that's why this statement is not 100% true. Okay? Yeah. When you not 100% true. Yeah. Not 100% true. I will give you that counterexample. Okay? Interesting counterexample. All right? Yeah. But the question is, if you know this statement is not 100% true, do you still feel it's useful? It's useful or not? Useful, right? If this statement is 90% true, 90% of the time true, 10% not true, do you feel it's useful? Good enough, right? Yeah, that's correct. Even if it's 90% true, we still feel it's useful. Yeah. So for that situation, so we call the statement like this, not 100% true, but still very useful. Because the percentage it is true is very high. 90% is pretty high, right? Yeah. So usually we call the statement like this as principle. Okay? Yeah. So this is the principle we want to follow. Okay? Although we say it's a principle, it does not guarantee it always correct, right? So when we say something, some principle thing, there is exception, right? Principle, so in general it's correct, right? For the principle, in general it's correct. Yeah. But there are some exceptions, right? Yeah. Yeah. So although you have some principle, in principle it's correct. But you may have exceptions. That principle is not correct, right? Yeah. So that's, in everyday life, we do it that way, right? Yeah. So here it's a principle. Yeah. So in general, we can follow that. But you need to be aware of there is some exceptions that may not hold. Yeah. But you need to be careful. Okay? That could occur. Yeah. All right. Let me give you that counterexample. The smaller size, the problem harder. The larger size, the problem easier. Okay? All right. First, we need to modify our understanding of the problem size. What do you mean problem size? What's the meaning of problem size? Okay? First, we need to understand that problem size. Problem size. Do you always mean the problem size, number of elements in the given array? Yeah. Number of elements in the given. Yeah. So far we're using that way, right? Number of elements in the given data array. Yeah. But there is another special case regarding the problem size. The problem size, other than the number of elements. Okay. So one meaning is number of elements. Okay? Yeah. So I do not write the whole thing. Yeah. But second meaning number two. This is meaning number one, right? Second meaning is the magnitude of the number. Also can be called the problem size. The magnitude of the number. Can be treated as the problem size. So what's that? The magnitude. How large is that number, right? Yeah. All right. So here. Because sometimes when we work on a computing problem, you are only given one number, but you need to do the calculation. Okay? For example, finding the Fibonacci number. You know Fibonacci number, right? Special number. You are only given one number. Okay? Give me Fibonacci number of 1,000. 1,000. I only give you 1,000. You need to tell me the value of Fibonacci number. This 1,000 is the problem size. The magnitude of 1,000, that's the problem size. Okay? I only give you one number, 1,000. You need to calculate the Fibonacci number. What is the Fibonacci number of 1,000? Okay? That's magnitude. Okay? Not necessarily an array. All right. Now, I want to use the example prime factorization example. So you're familiar with prime factorization, right? In prime factorization, given a large integer, now you need to do prime factorization, okay? To make it as a product of a sequence of primes. That's a prime factorization, okay? All right. Then, that one large integer, one number, the magnitude is the size of the problem, right? Yeah. Now, can you imagine for a smaller number, its prime factorization is harder than the prime factorization of a large number. Can you see that case? Yeah. All right, so I just give you an example. For a relatively small number prime factorization, let's say 357. How hard to factorize this number as a product of a sequence of primes? Okay, prime factorization. Yeah. Then I'll give you a larger number. Ask you to do the prime. Which one is easier? 1,000. 1,000 larger, right? If I ask you to do prime factorization, is it easier? Much easier than the prime factor of 357, right? Yeah. This tells you the problem size larger, it does not necessarily mean the problem is harder, right? Yeah. There are some exceptions. Here you have an exception. Okay? Yeah. So that's why this is a principle, all right? Not 100% true, but still valuable, right? In our problem solving, 90-something% is true. Still valuable, right? So we need to follow this principle, right? Yeah. All right. Just convey the idea. Okay. All right. So let's see how much time I have. Less than 10 minutes. All right. Yeah. So when some elements do not change the outcome, yeah. So that's the meaning. Yeah. Because after you do some work, as soon as you notice that for some elements, those elements cannot change the final result. Yeah. That could happen because you already find one element in the right place. So you do not need to touch it anymore, right? Yeah. So you can eliminate it. So if you find, so that won't change the final result. So you can safely exclude those elements from the consideration to reduce the problem size. Yeah. So that's the essence of this method. Okay? After you do it, you make your consideration pool smaller, right? Yeah, because you eliminate many unrelated elements. Okay, those elements irrelevant. Okay, you exclude those irrelevant elements. So your consideration pool becomes much smaller. So you can do better job, right? To process your consideration pool, right? Yeah. Yeah, that's the essence of this method. Okay? Yeah. Because later, yeah, at this point, I haven't assigned you many problem-solving questions at this point. Later, when I assign you more and more problem-solving questions, yeah, so you will reach this situation. So that is, yeah, because it's very easy. Yeah. Some of you just keep those irrelevant elements, because so they feel, oh, probably it's still useful. Right? So keep those irrelevant elements. Then you will see it's very likely you may do redundant work. Because those irrelevant work, if you do one comparison with irrelevant element, that's a redundant work. But you're not aware of it. When you keep the irrelevant elements in your consideration pool, you're not aware of them. Yeah. You assume they are normal elements. Okay? It's very likely you do some comparison with irrelevant elements. Yeah. So those comparisons are wasted. Remove immediately, okay, as soon as possible, to avoid redundant comparisons. That's the point, redundant comparisons. All right. Yeah. 8.2, impact of organized data. Yeah. So let me say something, yeah, if I cannot finish in a few minutes. So then we complete it next time. All right. Yeah. Problem number 5, element uniqueness problem. We need to solve a new, number 5 computing problem for this course. Element uniqueness. Given an array, this time we cannot assume distinct elements. Yeah, because you need to determine if there is any duplicate element. You need to determine. Okay? So here you cannot assume anything. Otherwise, you change the difficulty of the problem. Yeah. Yeah. So here, given an array, any arbitrary array with n elements, how to check if the elements are distinct? Simple question, right? Yeah. How to, yeah. So here we have several different algorithms to check if a given array have the distinct elements, right? And you want to find the best algorithm. Okay? All right. The first algorithm, before you have any idea, because usually when you have a question like this, at the beginning, you do not have any experience, right? Yeah. You don't have any experience. And you do not have any idea what you should do at that point. At the beginning, when you do not have any experience, and you do not have good understanding of the problem, what you should do. For a given computing problem like this, here I use this question as an example. Yeah. Backtrack. Oh. Yeah. Right. That's one of the problem-solving technique. Backtrack. Okay, one of the problem-solving technique. But it may not work for all the questions, right? Yeah. Some questions effective, but for some questions may not be effective, right? Yeah. Okay. Yeah. So here I want to talk about not specific technique. Yeah. Backtrack we can treat as a specific technique, right? And sometimes you can apply it, sometimes you cannot apply it. All right. So here I talk about the general methodology. All right. So not a specific technique, the general methodology. So when you start, you do not have a lot of information. and you do not have good understanding. Yeah. In that situation, the first thing you can try, apply the brute force method. Because brute force method, we do not need any technique, right? Yeah. You just do it in a straightforward way, right? No technique is needed. Yeah. If you need to use some technique, then people do not call it brute force, right? The backtrack we can treat as a special technique. If you use that, then we do not call it brute force. Brute force, essentially, no technique is used. Yeah. Just, plain straightforward. Here, can you use that plain straightforward method to check if there is? You can check, right? Louder? Yeah, doesn't matter. Yeah, good point. Yeah, probably take a while. But in our brute, when we look at brute force, we don't worry about how much time it takes, right? Because the brute force, we do not expect we can get a good solution from the brute force, right? But that's our starting point, messing around, right? Yeah. Because we want to get some hands-on experience. Yeah, so not necessarily a good solution. We don't worry about that. Just the one solution, okay? One solution. All right, let me leave this next time. Next time I want to talk about a little more on this brute force method, okay?